everyone that's here paying attention. Class.
Yes.
Very good. You have a stress ball. Very good. All right, so application carbon-14 dating. All carbon on Earth contains some carbon-14, which is radioactive. When a living organism dies, the carbon-14 begins to decay at a fixed rate. The formula P of T is equal to 100 e to the negative blah 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 gives the percentage of carbon-14 presented at time t years. Notice when t sub naught, t equals 0, right? My initial time. The percentage of carbon-14 present is 100%. When the preserved bodies of a 15-year-old, the 15-year-old La Donciella and her 2 children are found in Peru in 2005, 93% of the carbon-14 remained in their bodies, indicating that the 3 died about 550 years earlier. What is the rate of change of the percent of carbon-14 present in the 550-year-old fossil? So, we have a lot there to unpack. There's a lot going on there, right? Yeah. So, big story, kind of neat, right?
Why does she have 2 children when she's 15?
How long ago was this?
550 years old.
Okay, what year would that be?
I don't know.
What year is it currently?
It's 2024.
Okay, so 550 years earlier would be about,
1500.
okay, in the 1500s, what was possible in the 1500s?
Dating older people. Having babies.
At young ages.
That's-
Because the lifespan was only expected to be about 30 years.
But she's 52 kids? Is that even possible?
Yeah. Lifespan was expected to be 30 years.
does
So
that mean
for
the
that person, they were going through a midlife crisis.
And so she needed a baby.
No, she had babies beforehand. So, back in the day, you know, they didn't actually have an 18-year-old, I don't know, was it legal age or whatever?
Romeo and Juliet.
Yeah, you know Juliet was 13, right?
Oh.
Anyway, so we're gonna do the math to go along with this. Huh?
How old was Romeo? Is that why it's called the Romeo and Juliet law? Is
I
it-
think he was 16 at the time. Yeah, yeah.
That's crazy. That's
Yes, and there's a reason why there was a law based on it, but no one actually really thought about that.
Romeo and Juliet. About that. That's
'Cause it's
kind of weird.
forbidden
I
love.
thought like.
Yeah, it is forbidden. Stay away from those 13-year-olds.
Never.
It's wild to say out loud.
I know, right? Okay. Anyway, all right. So we're gonna do some rate of change. So we have a couple points of interest here. Let's go ahead and start this off. So, actually, do I have? Let me see. What do I have? Okay, there's the next page. So at times t equals 0, how much carbon-14 was there?
None.
100%, right? Okay. And that is carbon-14, which would be, and when T equals, how much was there? 93.5. So I have some points of interest now. Okay? I have some points of interest to go along with this. So this is actually, you know, we know that it is degrading, right? It is decaying. All right. Rate of change. What's the word rate of change mean? The what? The slope. Do we have 2 points? Okay, we have 2 points, don't we? So, we could actually just do a simple rate of change. So that would be 93.5 5 minus 100 over 550 minus 0, which is going to give me 6.5 over 100, which my rate of change is going to be, huh? Oh, I'm sorry. I was trying to divide. I'm kind of stupid right now. I haven't finished my coffee yet.
Get some coffee.
I know, I gotta make some coffee. So, that's gonna give me a negative, someone have a calculator? Come on, tree. Zero, 1, 118, like that? Okay, there we go. Let's go with that one. That's an 8 right there. My penmanship is just horrible though. Alright, so what does that mean though? This is an analogy and this goes along with the word problem. So what is it changing? Every year, very good. And this is percent per year. There we go. So that's a start. What is the rate of change of the percent of carbon-14 in a 2,000-year-old fossil? So what would I do? Would I do the same thing? Okay, so let's see what we get here. So if it's 2,000 year old, I gotta try and figure out how much is left, right? So I gotta plug it into my problem. So I know that T is 2,000. There is whatever percent left over. And I know that if I have my function, P of T is equal to, so P of T is equal to, what's that? 100 e to the negative 0.00121t. And P of T tells me, what does the P of T give me? Percent of carbon-14. That's important. So what it is that it's going to give me here. So it's percent of carbon-14 left. And that's what I'm looking for here. So I'm going to end up plugging in to my P of T. There you go. So it is P of 2,000 is equal to 100 e negative 0.000121,000. I'm going to pull up my calculator. there we go. What percent is left over? 78.506. 78.506. So after 2,000 years, I'm going to have 78.506% of carbon-14 left. Now, these problems, when you see these, they look super wordy, they look super crazy. Was it really that bad? So, going through my problem and reading specifically what it is I was looking for. Rate of change. Oh, rate of change means a slope. Okay. Rate of change of the percentage of carbon-14 left. Okay. So now, we now know what the percentage is, but now we still have to figure out the rate of change in between those two, right? Okay. So, at that time, I am going to rate of change there at 2,000. So this one right here, I'm going to go through and find the derivative for this one here. And I'm going to do the same thing for A here in a moment, and you'll see why. Okay. So now I have this value here that gives me my percentage. So let's go ahead, and if I do the slope formula, that's going to give me the secant line, right? Okay. That would be the secant line, and that would be the same thing that we did right here. So I'm going to show you the difference when we get to this next one here. So now, I want to know, since I have P of T is equal to 100 e to the negative 0.000121 t, this one right here, I'm going to do the chain rule on this. So if I do the chain rule, all this right here is going to be my u. So my u is negative 0.00121 t. My derivative is u prime is going to be negative 0.000121. Am I missing a zero here? I think I am. There we go. Yes. Then I come over to the side, and so I have equals 100 e to the u. The derivative of that is going to be p prime of t is going to be right here, 100 e to the u times du, which is going to be my negative 0.000121. And then I can go p prime of t 100 e to the negative 0.0121 t times negative 0.000121. So, can we do this all in our head? Hell no. Do we think we should have the calculator for this? Most likely. Let's try this. So let's figure out what it is when I find by P prime of 2000. So, start with my parentheses, negative 0.000121 close times 100 e raised to the negative 0.000121 parentheses 2000. There you go. So my rate of change now at that point is going to be negative, so it's going down 0.009499. The extra 9 is going to carry it over, and that's going to be 950. And that's going to be what? Carbon 14. Over a year. So now that I have the derivative, could I go back and do A? And I want to show the difference in between a secant line and a derivative at a point. So I can do this again, but now this one's going to be P, let me change colors to make this, of 550 copy and paste that, change this to so I have negative 0.0113. And I'm going to, is it 113 or am I missing a 0? There you go. So now I'm going to try and put this in the calculator so you could actually see the difference in these different things. Now, what type of equation is my original function? Is it exponential? Is it raised to a power? Yeah. So it should look like some type of logarithm. Alright, so I'm going to go to here. I'm going to graph my original, which is going to be 100 e to the negative 0.000121. Okay, I don't see anything there. What would my domain of this one here be? So t would start off at 0, right? And then how far should I take out my t? Because t is replaced with x. So to get this in my graph, I should at least go to 2000, right? Okay, so I'm going to go to Menu, Window, Settings. I'm going to start at 0. And I should at least go to 2000. I'm going to go slightly above because why not? My y values. am I gonna have negative? What does the P of T represent? The percent of carbon, right? And my percent should start at 0 and go to probably 100, right? Okay, because it is going down like that. So it is gradually going down. So it looks like it's a straight line, but it's really not. Now I'm going to put in the next one, which is going to be my derivative menu. Tab. The negative, so parentheses, negative 0.000 to 1 close times 100 e to the negative 0.000 Okay, so for the slope, it's going to be super tiny, right? So all the slope is going to be right down in here, and they're going to be in negatives. That's why I can't see these, because it's going down here. So what I'm going to look at is, this is going to be one of those things that the calculator does for you that you guys should check out. Menu, analyze graph. I want to find the dy dx. I want to find the slope at a single point. So dy dx, and the point that I wanted to find, what was my first one? Was it 550? There you go. So isn't this what we had? Yeah. All right, let's check it again. So menu, analyze graph at 2000. There we go, right there. Now, what can you tell me about this graph? What is it doing over time? The graph is going down, right? Okay, can you tell me any characteristics of it going down? It's going down at a, is it increasing rate? Decreasing, so it's leveling off here. So it's going down at a decreasing rate. So if I take this out even further, let's change it to 10,000. Actually, no, let's go 50,000. Oh, sorry. I'm kind of stupid. Sorry. 5, 0, 1, 2, 3. 50,000. There we go. There is my nice logarithm. So it is decreasing. It's going down at a decreasing rate. So it's leveling out to the point where it actually gets way down over here, right? Now, does that make sense, or is that just a whole bunch of nonsense that I showed you guys? Because I wanted to show you guys the different things that this calculator can do, and when you were able to graph it, it could actually help you by finding a slope, especially on these problems that are kind of weird. So, can you use your calculator to test your answers? Yeah. Can you use it all the time? No. You got to learn how to do the math too. So, other than that, was that my last slide? No? Yeah? No? Okay. So, we got another one here.
We got 9 more slides.
9 more? Okay. That's what I figured. All right, chain rule, prime or Leibniz notation. Now, this is kind of what we've been doing. I don't really like the way that it actually f of g of x. It's kind of weird because I always see this first one as fog. I don't know why. I always see it fog. All right, suppose h is equal to f of g. Find h prime. Given that, okay, so in this case, I gotta actually do these things. So we're gonna say f is one thing, f prime, g, and g prime. So f prime, and here's another one of two, g prime. So I'm going to rewrite my notation on this one so you guys can see. So if I'm rewriting the notation, right here it says g prime of x there we go. And in this case, this is going to be equal to h of x. So, let's go ahead and start off with what I have here. G prime of x came out to be, my x is 1. Okay, so g prime of 1. So g prime of 1 gives me -3. This right here says g of x. So if I plug in 1, if I plug in 1 right here, what is g of 1? 2. So now this is going to say f prime of 2. So f prime of 2 is going to give me -4. So as I multiply together, I could say that h prime of 1 is going to be +12. Now, these problems get me all the time. That's the reason why I have to write down every single step, every single notation on each of these. I have to list them. Okay? I gotta show all my work. No matter how many years I've been doing this, I still have to show all my work. Alright, questions over that? Are we okay? Maybe? Because I was thinking of picking up the rest of this tomorrow, because the next ones are going to be kind of crazy. Yes, no, maybe? Okay, so we'll pick it up tomorrow. Make sure you guys all like, share, and subscribe. Hit that notification button.